This is SPH4C. It's the second lesson. Today's lesson is about distance and displacement. Distance is a scalar quantity, so from the last lesson, remember, scalar quantities don't have a direction, and displacement is a vector quantity. It does have a direction. So let's start with, before we get there, perspective. So one of the important concepts is perspective. Right now, you're looking at Einstein here. And say hello, Einstein. Einstein, you're seeing him from a side view. So to give you some idea of how orientation in space works, I have here a compass. It's a pretty straightforward compass. What it is, it's a piece of metal here that's magnetized. It's free to move around, and that's what a compass is. A compass is a magnet that can move freely. So a compass is a magnet that can move freely. And so this magnet is starting to settle down, and this end of this magnet, this part of the compass, this one, this end always points towards the Arctic. This end that has a little white tab on it always points towards the Antarctic. The Arctic is north of us, the Antarctic is south of us. So when I point this way, I'm pointing towards the north. And that means that this direction where I am right here is roughly west, and this is east. So we're going to pretend for now that I've got this oriented in a west-east direction. So just from a perspective, first off, let's just say that this is roughly west and this is east direction. Then this would be Einstein moving in the west direction. But the thing I want to focus on is your point of view. Your point of view right now is a side view of Einstein. What if you could look from above? How would you draw that? So right now we've got Einstein, here he is, and he is moving like so. This is a side view. Let's take a look at what an aerial view would look like. So what you right now has an aerial view. And these perspectives are going to be important when we look at the movement of objects. We're always going to have to decide whether we're looking at aerial view or a side view. So if Einstein was to move up, he would do this. That's up. This is down. This is west. This is north. This would be south. And towards me would be east. So we could draw a grid like this. So now I'm going to use an aerial view I'm going to draw to explain a concept about Einstein and his motion. Let's pretend Einstein began here. So this is where he began. This is his beginning. And let's imagine he went on the journey like so. And he finished here. Einstein has moved in 2 dimensions. So here's where he began, here's where he finished. Now let's imagine that this was pointing the following way. Let's imagine that this was north, it's not up, this is south, it's not down, this is west, this is east. We're looking as if we're birds down on Einstein. And as he moved from this beginning to finish, we could measure the length of this path. The length of this path that he traveled, that's what we call distance. It measures how far he went. The unit we use to measure distance generally is the meter. It has the symbol small letter m. It can't be a big M, it actually matters. It's a small letter m that you use for meter. And if we took a piece of string, we could measure how long this path is, and then we could state the distance that Einstein traveled. So I'm going to measure how far he actually traveled. I don't have string, but hey, I have a power cord, so I'll use it. So I start here, I move the cord around, tracking where he traveled. Track, 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 and it got to roughly here. Now I go to the ruler and I measure how long that track is, and it was 82 centimeters. So the total distance he traveled was 0.82 meters. So he traveled a total distance of 0.82 meters. That's a scalar measurement. Now let's do is introduce the vector measurement. The vector measurement is something called displacement. What displacement measures is displacement measures the length of a line segment from the beginning to the finish. So if we draw this line segment in here, and I'm just going to quickly do that here. If I draw in the line segment here, that measurement is different. That measurement is telling us how far from the beginning to the finish has he been displaced. He didn't actually travel along this line, but if we only look at the beginning and we look at the finish, this is the shortest amount of space from where he began to where he finished and the direction that it pointed in. And as you can see, if you look at this direction, it's pointing roughly somewhere like that. The direction that he's moving in seems to be slightly to the east and slightly to the south. If we could measure this angle in here, this angle right here, we would know how many degrees from the east to the south that Einstein was moving in, and we can measure this length. So I'm going to measure this length right now, and this length is 0.4 meters. So this is something called displacement. And the symbol we use is a delta D with an arrow on the top for vector. And he was 0.40 meters. And now I've got to find out how many degrees from the east he was towards the south. So now to find the direction that his displacement points in, I take a protractor. This is a circular protractor. I'm going to go back to the beginning, and I'm going to line up the east and west axis and the north and south axis with it, and I'm going to measure how many degrees from the east Einstein traveled, and it looks like 10, 20, 25 degrees. So when I measured the degrees in here, because this is pointing east, when I measured the degrees in here, it worked out to be 25 degrees. So the way I would write this is east 25 degrees towards the south. If I was to measure the angle in here, I would discover that this is a total of 90 degrees here, so this would have to be 65 degrees in here, because the total of these two together comes to 90 degrees. So I could write this as south 65 degrees east. You don't have to worry about that too much. We're always going to be moving in a straight line. In this course, we're not going to really be deviating off in multiple directions, but that's just to give you a sense of how it's done. So two concepts we have today. We have distance and displacement.